Okay, let's get started. Hi everyone, welcome to CS330. If you're expecting to be in a different class, then you're probably in the wrong place. I'm Chelsea Finn, I'm a professor in the computer science department. So let's get started. So first I'm going to go over course logistics, and then we'll go over a little bit of content to get started on some aspects for motivation for why we care about multitask learning and meta learning. So first, for logistics, some information and resources. So this is the full staff for the course. We have 4 TAs. I think 1 or 2 of them are here today. Maybe you can kind of stand up and introduce yourself.
Yeah,
And then great. So those are the first and last one, and able to make it today, but they're also TAs for the course as well. There'll be great resources for you as you go about taking the course. The course website is shown here, and there's a lot of information on the course website beyond what we'll be kind of covering in the logistics here. Also, we have a piazza. This will be for questions as they come up in the course. This is the staff mailing list as well, and each of us will be holding 1 hour of office hours per week. My office hours are Wednesday after class, and the other office hours will be posted on the course website. We'll have office hours for the first time on Wednesday this week. Great. So prerequisites and enrollment. The main prerequisite is machine learning experience, basically, covering machine learning and reinforcement learning, CS330 or equivalent. We highly recommend having some previous reinforcement learning experience because a large portion of the course will include topics in reinforcement learning. If you're not currently enrolled, please fill out the enrollment form on the website. And we will kind of go through that. We do still have some open spots in the course, and we'll go through that probably around Tuesday or Wednesday this week, so please fill that out as soon as possible if you're not enrolled. And then if you filled out the form and didn't receive a permission number yet, it's either because you filled out the form very recently or because we weren't quite sure if you had the kind of necessary experience in order to succeed in this class. We'll get back to everyone by Wednesday this week. Okay, all the lectures are being recorded, and the lectures will be internally released on Canvas as soon as the recording is available. They'll also be publicly released after the course for the benefit of kind of the general public. Despite this, kind of things like student anonymity will be preserved in the recording. And so please still feel free to ask questions throughout the course as well. There are around 20 remote students from the Stanford Center for Professional Development that are joining the course as well remotely. And SCPD is actually the folks that will be allowing for us to release all the videos online after the course by providing captioning services and other things. So if you have any questions about anything up here. Okay, assignments. So the assignments will all require training neural networks using TensorFlow. And so if you're not familiar with TensorFlow already, we'll be holding a review session on Thursday of this week. And basically, you should be able to understand kind of an overview of TensorFlow. And if you don't understand an overview of TensorFlow, I'd highly encourage you to go to the review session and ask plenty of questions. This is kind of your opportunity to get information about how to use TensorFlow if you aren't familiar with it already. Topics that we're covering in this course. So the types of topics, these are all listed, all the kind of lecture topics are listed on the course website. It's going to include things like what is multitask learning and meta learning, the basics of these algorithms, including various approaches ranging from black box approaches, optimization-based approaches, metric learning methods as well. How we can view these types of methods in a hierarchical Bayesian framework as kind of learning priors over multiple tasks and using those priors. Topics like multitask reinforcement learning, goal condition reinforcement learning, hierarchical reinforcement learning, topics in meta reinforcement learning, as well as some open problems, invited lectures, and research talks from faculty in the field. One thing worth noting here is that there'll be an emphasis on deep learning, as kind of indicated by the title of the course, as well as an emphasis on reinforcement learning. So a little under half of the course is going to be kind of focusing on different topics in reinforcement learning, because that is where some of these types of techniques become a lot more interesting and a lot more challenging. Topics we won't cover, due to kind of the constraints of how much time we have in this course, we won't cover topics in AutoML. This includes things like architecture search, like hyperparameter optimization, and learning optimizers. But beyond that, I think we'll be covering most topics in meta-learning and multitask learning. But we'll also have an emphasis on deep learning approaches, so we won't be thoroughly covering things in things without neural networks, for example. And I'll kind of describe why later in this lecture. Okay, so the course format. So we'll have 3 types of course sessions. We'll have 9 lectures that are kind of given by me. We'll have 7 student reading sessions, which will consist of presentations by you presenting different papers, and we'll have a discussion of different papers in the multitask learning and meta-learning literature. And then we'll also have 3 guest lectures. All students that are enrolled in the course are responsible for giving 1 group presentation of a paper. And in these kind of student reading sessions, we'll be presenting 4 papers, and the papers are all posted on the course website. And also further instructions on how to actually prepare your presentation is also posted on Piazza. And beyond, even if you're not presenting a paper, we highly encourage actually to participate in the discussion of the paper and come to class. So while the courses are being recorded, I think that you'll actually get a lot more from the course if you actually actively participate in various discussions of papers to better understand the literature and kind of dig into why these papers are good or what their limitations are. Okay. And also this will change in future offerings. So in future offerings, we'll probably be introducing more lectures into the course and fewer student reading sessions as years go on. Okay. More details on assignments. So we're going to have 3 homework assignments. The first homework will cover things ranging from multitask data processing and black box meta-learning methods. So you'll actually be implementing how to actually kind of go about processing data in a multitask fashion such that you can apply these types of algorithms to them, and also implementing a black box meta-learning algorithm. In homework 2, you'll be implementing gradient-based meta-learning algorithms as well as metric learning algorithms. And then in homework 3, that will be on things like goal-conditioned reinforcement learning and multitask reinforcement learning. So you'll get the opportunity to play around with all of these algorithms yourself and see how well they work on various domains, including like image classification domains and simulated robotic control domains. And then lastly, we'll have a final project. So this is going to be a research level project of your choice. We encourage you to kind of integrate any kind of research that you're doing into this research project for the course, as long as it's on the topics that are kind of pertinent to the course, things like multitask learning and meta-learning. And for this, you'll be allowed to form groups of 1 to 3 students. And you're welcome to start early, so you're welcome to kind of start forming groups now and start thinking about what you'll actually want to do for your final project. For grading, it'll be 20% on your paper presentation, which is in a group, 30% on homework, 10% each, as well as 50% on the final project. Okay, and then you're also given 5 late days across homeworks and your project paper submission that you can kind of allocate as you see fit, depending on things coming up. Great, and then the last thing, I guess one more thing about the project is that we'll also be posting kind of guidelines for the project, and we'll have various milestones throughout the course for you to propose your project, kind of communicate progress that you've made on your project, and then of course present the final project. The things that you need to do today are sign up for Piazza if you haven't already, fill out your paper presentation preferences. So we have 7 paper presentations with 4 papers each, so fill out your preferences for which of those 28 papers you're most interested in presenting. Do this by Thursday so that we can try to get kind of assign those as quickly as possible, especially for the first presentation, which will be happening next week on Wednesday. And so the instructions for the presentations and also how to sign up is on Piazza. And then lastly, start forming final project groups if you want to work in a group. And if you're not familiar with TensorFlow, review the TensorFlow intro or go to the review session on Thursday. Okay. Anything else about logistics? Any questions? Yeah. So we will be providing a lot of infrastructure around around these kind of different problems in TensorFlow. If you want to do everything in PyTorch and kind of produce the deliverables that the curves that you need to deliver and produce as part of your write-up of the assignment, that's fine. That's completely fine. So if you want to only use PyTorch, you can do that, but it will probably involve writing a fair amount of code in addition to the code that you would have to write in TensorFlow because of the infrastructure being written in TensorFlow. Yeah.
Are all the homeworks runnable on laptops, or does it require GPU?
So the first homework will be runnable on a laptop. The second homework will be a little bit more compute heavy, and we're still looking into various cloud compute options for that we'll be able to provide for people that don't have GPUs, for example, to be able to run their code on. And the third one will probably be runnable on a laptop as well, but we're still finalizing that assignment. Yeah.
Will we be using TensorFlow 2 or 1.14?
We'll be using TensorFlow, but not TensorFlow 2. Yeah.
What's the policy on sharing final projects with potentially other classes?
That's a good question. Let me get back to you on that. We'll post that on the project guidelines on kind of what we allow in that regard. Okay. Two more things. First, ask plenty of questions. You guys are off to a great start. I mean, this course is really for your purpose, not for my purpose, just to stand here and talk. And so if there are things that are unclear, things that you're kind of curious to learn more about, please raise your hand and ask questions. And second, this course is new. It's the first time that we're offering it. And so as a result, the course will likely be rough around the edges in comparison to courses that are run every single quarter. And so please bear with me and the rest of the course staff. And this is kind of all the more reason for you to ask plenty of questions as we kind of figure out how the course is going to be run throughout the quarter. Okay, great. So now I'd like to talk about, why should we actually care about multitask learning and meta learning? And what are the sorts of things that you'll actually be learning in this course? And what I'd like to start this discussion with is actually talk about some of my own research and some of the reasons why I care about multitask learning and meta learning, and then I'll talk about kind of more broadly where these types of algorithms are being used and why they're really important and a really fundamental aspect of machine learning research. Okay, so one of the questions in my research group that we like to think about is how can we enable agents to learn skills in the real world? And what I mean by the real world is I mean robots. Robots like these, robots that can use tools to lift up objects and put them into bowls, that can play with children's toys, that can watch kind of a video of a human doing something and learn from that. And you might ask, well, why robots? It seems like robots might be a lot of work to deal with. And I think that the reason why studying robots is really exciting is that robots can teach us things about intelligence. Now, okay, this might sound a little silly also because robots are not very smart. But I think that robots are faced with many of the challenges that humans are faced with as they learn and develop over the course of their lifetime. Robots are faced with the real world, and they have to deal with it. Robots have to be able to generalize across tasks, across objects, across environments in order to be successful in real-world settings. They need some sort of common sense understanding in order to do well. And lastly, supervision can't really readily be taken for granted. It's not easy to just provide labels or even figure out what labels mean in the context of getting a robot to do something. So I think that if you can build intelligent robots in the real world, you can kind of convince yourself that you've solved some important problems regarding intelligence. Though, of course, my goal in this lecture isn't to convince you to work on robots. My goal is instead to kind of discuss some of the challenges that come up and kind of guide this towards multitask learning and meta learning and kind of describe where this fits in. So I want to start with a bit of a story here. So at the beginning of my PhD, like 5 or so years ago, I was in a lab at Berkeley, and there was this research project that was going on. Whoops, the video isn't playing. Here we go. There's a research project going on trying to get the robot to learn how to assemble this toy airplane by putting the wheels into the correct position. And the robot here is learning how to do the task through trial and error. At the beginning, the robot is kind of started with very random motions, and over time is able to kind of figure out how to do the task successfully. So I thought this is really cool. The robot is actually kind of, you can see it kind of learning really, this is 20x real time, but if you kind of watch the robot in real time, you'd actually be able to see the robot learning in real time through trial and error. I guess what's really exciting about this is the robot isn't just this isn't just an algorithm for learning how to do that task. It's an algorithm that can do really a wide range of manipulation tasks. And so in principle, this algorithm could be applied to a wide range of settings. Now, one of the things that was a little bit disappointing about this is that it turns out the robot essentially had its eyes closed. It was doing this completely blind and just kind of essentially blindly trying to get the wheels into the right place. And so kind of this motivated some of the work that I did at the beginning of my PhD, where we wanted to get the robot to do things while also seeing, do things that required vision. In this case, it needed to actually see to figure out where the shape sorting cube was in order to figure out where to place it. And again, here you can see it kind of learning over time, starting from scratch, figuring out how to get the block into the respective hole. And so I guess one of the things that I mentioned here is that kind of the reason why these sorts of algorithms I think are really exciting is that the same sort of algorithm, the same reinforcement learning algorithm can be applied to many different tasks. So you don't just learn how to insert the block into the shape sorting cube, which it kind of eventually figures out here. And here's actually the kind of the final policy where I'm holding the cube in front of the robot. It can also be applied to learn things like placing the claw of a toy hammer underneath a nail, or screwing a cap onto a bottle. Or kind of the most challenging thing that we got it to do with this particular algorithm was to use a spatula to lift up an object into a bowl. And this task is actually really challenging because the robot has to be fairly aggressive in maneuvering the spatula underneath the object. So this was really exciting. At least we were really excited about some of these results. And there were a range of other people that built upon the method as well, getting robots to do other tasks like using a hockey stick to hit a puck into a goal, opening a door, throwing objects. And so while it kind of seems like this is pretty exciting, and indeed at the time it was very exciting, we have a bit of an issue. The issue is that the robot didn't learn how to use spatulas to lift objects into bowls. It learned how to use that spatula to lift that object into that bowl. And if you gave it a different bowl or a different spatula or even a different tablecloth in the background, the policy wouldn't generalize. The policy would fail because it was trained in exactly that environment. So this doesn't necessarily seem like that much of an issue. So you could just say, well, why don't we just give the robot more spatulas and more bowls and more tablecloths and have it just learn in more settings. And maybe this is kind of an easy problem to solve. In many ways, you would be right. That would kind of be a reasonable approach to try to learn a more generalizable policy. But the tricky thing is that this algorithm was designed kind of with the intention of it being a single task learning algorithm in a single environment. And so let's kind of look at this. So behind the scenes, if you look at one of these algorithms, especially algorithms that kind of require moving objects in different ways, this is kind of what the learning process looks like. Behind the scenes, the robot kind of tries to do the task, and then a human comes in and puts the puck back. And so by nature of kind of focusing on this single task learning problem, the methods aren't actually scalable to learning more tasks without actually starting again from scratch and having my friend Yevgen here kind of repeatedly reset the robot after each trial. And so Yevgen here is doing more work than the robot, arguably. And it's also just kind of more generally, it's not practical to collect a lot of data this way. So to build algorithms that are effective at learning across many different tasks, we need to, in many ways, fundamentally rethink how we're actually kind of designing these algorithms in the first place. So kind of the issue here was that it relied on very detailed supervision, very detailed guidance that can't be scaled to many different tasks. And this is not just a problem with robot learning, it's also a problem with kind of standard reinforcement learning algorithms as well. kind of things that learn how to play Atari games and locomotion, they require a lot of data, a lot of supervision in the form of reward functions in order to learn effectively. And it's also not just a problem with reinforcement learning. So if you think about some of the biggest successes in supervised learning systems, these systems are able to handle much more diverse data and learn across different users, different languages. But in many ways, these systems are still learning one task, starting from scratch with very detailed supervision. So essentially, these systems are what I would call specialists, in that they're trained for kind of in a single task learning setting. And instead, if we kind of think about, well, how could we get a more generalist system? That's kind of, in many ways, part of what this course is about, in some ways. And kind of one way to get inspiration for this is we could look at kind of how humans learn. Humans don't learn in the settings that I mentioned before. Humans learn kind of by rolling around on the floor, by interacting in kind of a very rich and diverse environment. Humans are what I would call generalists. Humans learn many simple skills, such as crawling, picking up objects, playing with toys, before trying to learn much more complex tasks. And perhaps to build machine learning systems that are generalists, we need them to look a bit more like this. Systems that can build upon previous experience to learn new things more quickly and learn many simple things before trying to learn more complex things. And so if we make an analogy to the way that machine learning systems learn to how humans learn, this would kind of be like if we wanted to train a system to play Go from scratch, this would be kind of like trying to start from scratch and have a baby learn how to play Go, for example. And so this seems a little bit silly or a little bit off in some ways, potentially. Okay, so that's a bit why, some of the reasons why I care about multitask learning and meta learning. Why should, even if you don't care about robots, why should we generally care about these algorithms? And unfortunately, there's a lot of reasons to care beyond robots and beyond kind of trying to build more general purpose machine learning systems. And first I want to start by why do we care about deep multitask learning and meta learning? Why do we care about deep learning in particular? Actually, before I move on, are there any questions on the part that I mentioned before, on the robots? Okay. So if we kind of go back at this point, like 10 years, the standard approach to computer vision looks something like this, where you took some image, you then tried to extract some mid-level some features, such what were things called hog features or SIFT features. These are features that are designed by hand by researchers. And then on top of those features, you may have more mid-level features like deformable parts models, kind of as visualized on the right. And then on top of that, you would have a little classifier, like a support vector machine on top of those features. And now if you kind of fast forward 10 years until now, basically what modern computer vision looks like is something that is more like this. Something where you take an image and you pass it through a neural network and have it produce the desired output. And essentially kind of one of the most salient differences between these two things is that deep learning allows us to handle unstructured inputs. It allows us to operate directly on the image pixels that are shown on the left. It allows us to directly operate on things like language, like sensor readings, without requiring hand-engineered features like hog or SIFT or deformable part models. And also with less domain knowledge. So it means that we can kind of apply this single class of techniques, of neural networks essentially, to a wide range of problem domains. So that's one kind of benefit of deep learning systems. And the second benefit, of course, is that they work really well in a variety of different situations. So if you look at results on the ImageNet dataset over the course of around 5 years, and look at the error rate, this dot right here is AlexNet in 2012. This was in many ways one of the first neural networks that was successfully demonstrated on the ImageNet dataset. And before that, things were plateauing around 0.25, 0.3. And then kind of there was this this mode shift, this kind of mode transition, where after 2012, I think most, if not all, of the dots are deep learning models, and of course were way more successful than previous approaches that were relying on hand-engineered features. And this isn't just specific to computer vision. So in machine translation, for example, in 2016, Google started switching Google Translate to a system based on neural networks. In this case, PBMT is phrase-based machine translation, whereas GNMT or NMT, more broadly, neural machine translation, starts using neural networks. And we see a pretty big difference. This is showing the human evaluation scores. We see kind of ranging from 50% to 80% improvements by using neural networks. Okay, so this is why deep learning, and kind of in 2 slides, there are other reasons as well. Now, why deep multitask learning and meta-learning? So if there's something that we've learned from deep learning is that we can, if we kind of give these neural networks large and diverse data sets, they can achieve broad generalization. So for example, the ImageNet data set, or things like transformers, GPT-2, these have been kind of extremely successful at producing models that generalize across many different images, across many different inputs. But the caveat is that they require a large and diverse data set. And what if you don't have a large data set? Then you're in a bit of trouble. These are domains, and there are a wide range of domains where we don't have large data sets. Things like medical imaging, like robotics, like I mentioned before, like education, you don't have a lot of data for each individual student that you're trying to teach. Medicine, recommendation systems, translation systems, we don't have a lot of paired data for every single pair of languages that's out there. And so as a result, it's impractical to learn from scratch for each disease, for each robot, for each person, for each language, really for each task. And so instead, that's where these multitask learning techniques can come in. So beyond the kind of the settings where we don't have a large data set, what if your data has a long tail? What if your data distribution looks something like this, where the y-axis is showing the number of data points, and the x-axis is showing different objects that you've encountered in the world, or different interactions with people, or words that you've heard over time, or driving situations, etc. When you're in kind of a variety of the situations on the left, you're kind of in good shape. This looks a lot like what you've seen before, whereas if you're on the right, in the kind of the tail on the right, that's where these algorithms start to break down, where supervised learning methods really struggle to perform well. And this is, for example, this is a really big problem in autonomous driving, where cars can handle a wide variety of very common situations, but when they see very weird situations, humans can handle them perfectly well, but these cars really struggle. Okay. And then lastly, what if you need to quickly learn something new? What if you have previous knowledge and you want to learn something new about a person, for a new task, about a new environment, without training from scratch? It turns out that people are pretty good at this. And in particular, let's see how good you are at it. So I want to give you a little test. The left side is showing your training data. There's 6 data points. You have 3 paintings that are from Braque and 3 paintings that are from Cezanne. And your goal is to be able to classify the test data point that is on the right. And so if you think the painting on the right is from Braque, raise your hand. And if you think it is from Cezanne, raise your hand. Great, okay. I think that there are more for Braque, which is the correct answer. And the way that you can tell that is you can kind of look at the types of kind of straight lines and curved lines that are prominent in the image. And so how did you actually go about doing this? So this is the kind of problem that's known as few-shot learning, where you're only given a few data points, in this case 6 data points. And your goal is to make predictions about new data points from that very small data set. The way that you accomplish this is that you weren't learning from scratch. You have previous experience. You haven't probably seen these exact paintings before, and you probably haven't necessarily even seen paintings from these painters before, but you've seen paintings before. You've probably seen kind of, you know what objects are, you know what textures are, and through that previous experience, you were able to quickly identify the painting corresponding to the correct painter. Okay. So all of these things, if you want more general purpose machine learning systems, if you don't have large data sets, if your data has long tails, if you want to be able to quickly learn something new, these are all settings where elements of multitask learning and meta learning can come into play and can help us out and basically make machine learning more effective in these problem settings. Any questions on these 4 things before I move on? Okay. So I've been talking a lot about multitask learning, but what is a task? And this is actually something that's really important because a task isn't necessarily what we kind of associate with in kind of the English language. For now, the way I'm going to define a task is something that takes as input a data set and a loss function, and gives you a model. We're going to kind of generalize this later and make it potentially a bit more formal later in the course. But for now, this is what we're going to be considering. Essentially, you can view a task as a machine learning problem, where you have some data, have some loss function, you want to optimize that loss function in order to produce a model. And so what this means is that if you have different tasks could vary in different ways. They could vary for different objects, like maybe one task is to kind of be able to classify between one type of cat and another type of cat, whereas another task corresponds to being able to classify between different types of water bottles. So in this case, different tasks would correspond to different objects. They could also correspond to different people if you want to be able to kind of personalize these systems to be able to handle and effectively make predictions about new users. They could correspond to different objectives. Maybe in one case you want to be able to classify classify someone's age versus you want to be able to classify someone's height from an image. Those are kind of different objectives that you want to be able to accomplish. It could be something like different lighting conditions of your model, different words that you're encountering, different languages that you're encountering. It can encapsulate kind of a wide range of different things. So not just different tasks as you would think of a task as in English. Really, it can vary in a wide range of ways. Questions on that?
So is it like a different distribution of the data set and the loss function? Or?
Yeah, so it could correspond to a different data set or a different loss function or both. So for example, in the case where you have different objects, that would manifest in potentially the same loss function, but like be able to match labels, but a different data set. Whereas something that looks like different objectives, like classifying between one thing versus another thing, that might be something that looks like different loss functions, but the same data set.
So in this case, when we're talking about the loss function, we're not talking about like cross entropy. We're talking about like ground truth versus data set, that sort of stuff, right?
Yes, I think that is the case. You could also have one task that has like a cross entropy loss and another task that has like a mean squared error loss, for example. Although of course you could generalize both of those as like log likelihood.
Okay. But that, I think when we're talking about different tasks here, we're not talking about that.
Yeah.
Okay.
Yeah.
Data point we call as a task. So let's say I have a network which is going from a circuit specification to a circuit. Given a new specification, can you say that that's a new task?
Yeah, so you could say that is precisely a new task. You could also, I think that there is kind of this fluid notion of what is a new task versus it's just kind of lumped into a single task learning problem. And I'll actually talk about that kind of more, that fluidness in a couple slides. But that is kind of one thing that you could view as different tasks. Okay. So in multitask learning and meta learning, there's one critical assumption. This is kind of where some of the bad news comes in, which is that different tasks need to share some structure in order to get a benefit from these algorithms. If the tasks that you're trying to learn across don't share any structure, then you're better off just using single task learning independently on each of those tasks and kind of then morphing those into a single model if you want to produce a single model. The good news is that there are many tasks in task distributions that have shared structure, even if they don't kind of on the surface appear to have shared structure. So as one kind of simple example here, something like screwing a cap onto a lid versus screwing a bottle cap versus screwing kind of a pepper grinder. all share a similar structure in terms of the underlying motion that needs to be performed. This is maybe an example where the shared structure is more explicit. And even if there are tasks that are seemingly unrelated, there is things that are still underlying, so there is structure that's still underlying those tasks, because the laws of physics are kind of underlying the real data that we have. People are all organisms that have intentions, and so even if two people are very different, they still have some commonalities. The rules of English are underlying all, well, not all, but a fair amount of English language data. And languages are kind of developed for similar purposes, and so on. So these kind of may seem like superficial relationships between different tasks, but in reality, this leads to far greater structure than having completely random tasks. Because completely random tasks would essentially look like completely random inputs, random labels, and in practice, kind of the real world is underlying a lot of the data that we're looking at. Yeah?
Are these assumptions or kind of motivation guided just towards multitask? I mean, are you separating mental learning and multitask as completely kind of like different things, or is this mental learning?
It applies to meta learning as well, yeah. So I'll give problem definitions of multitask learning and meta learning on the next slide, but in essence, meta learning is all about kind of learning the structure underlying tasks such that you can more quickly learn a new task. And if there isn't any shared structure, then you won't be able to learn more quickly than learning from scratch. Okay. So let's informally go over some of the problem definitions. In the coming lectures, actually in the next lecture, we'll formalize these lectures, these problem definitions a lot more. But just to give you a rough idea of what I'm talking about with these kinds of problem definitions, here's kind of roughly what things look like. So you can think of the multitask learning problem as trying to learn all of the tasks that you're provided with more quickly or more proficiently than learning the tasks independently from one another. And then what the meta learning problem is looking at is given data or experience on a set of previous tasks that you're given, you want to be able to learn a new task more quickly and or more proficiently than learning from scratch by leveraging your experience on the previous tasks. So essentially the difference between these two things is that the first one you're trying to learn a set of tasks and do well on those training tasks. And then in the second problem setting, you're trying to use experience on training tasks in order to do well at new tasks. And in order to basically be able to more quickly learn new tasks given a data set. And in this course, we won't necessarily be covering everything that's considered a multitask learning algorithm or a meta learning algorithm. Will be really anything that solves one of these two problem statements will be fair game for including in the course. So things that allow you to build on previous experience to quickly learn new tasks, even if they aren't through learning to learn techniques, I'll try to touch on them in this course. Questions on these problem statements? Yeah?
How does meta learning differ from transfer learning under this definition?
Yeah, so I guess in many ways I think that this is a form of the transfer learning problem statement where you want to take some data and use knowledge acquired from that data to do well at other tasks. I think that one aspect about this problem statement is that you want to be able to learn a new task more quickly, whereas in transfer learning, you may also want to be able to just perform a new task well in zero shot, where you kind of just want to share representations. I actually kind of view transfer learning as something that encapsulates both of these things, where you're thinking about how you can transfer information between different tasks, and that could actually also correspond to the multitask learning problem, as well as the meta learning problem. Yeah?
I thought meta learning was kind of like learning to learn. Would you say that is kind of like a consequence of that definition, or kind of like a super path?
Yeah, that's a good question. So I guess what I'm defining here is the meta learning problem, and I think that meta learning algorithms are all learning to learn, and they solve this particular problem. And they're not the only way to solve this particular problem. Does that answer your question?
So there could be no meta learning with one single task?
That's a good point, yeah. So in principle, you could still perform meta learning in the context of a single task. And what you would be doing in that case is probably actually in some ways breaking down that single task into subtasks or into kind of subcomponents, and then using that when you're facing something new in that single task, using that experience to more quickly learn in the future. Yeah, so that's a good point. The tasks in some ways could be something that's kind of latent to your underlying problem. Yeah.
The meta-learning problem strikes me as quite similar to the problem of domain adaptation.
Mm-hmm.
Are they the same, would you say, or are there some clear distinction?
Yeah, so I'll formally cover the distinction with domain adaptation in the next lecture, but in some ways they're similar. I guess in some ways one is more specific than the other, and in some ways it's kind of the opposite. So in domain adaptation, you typically do want to it's kind of a form of transfer learning in some ways, where you want to transfer from one to another. One thing, and I guess when I get into the more formal definitions of these problems, this will become more clear. One thing you typically see in the meta-learning problem is that the tasks that you're seeing at test time, you assume to be in the distribution of the tasks that you're seeing during training, whereas many techniques in domain adaptation are considering a setting where your test domain, it may be out of distribution from what you're seeing during training. And yeah, so that's in many ways one of those distinctions there. Okay. Now, one question that was asked a bit before is kind of, I think it was in the context of circuits, is what is something a single task learning problem or a multitask learning problem? And in some ways, this gets down to the question of, doesn't multitask learning reduce to just a single task learning problem? And in particular, what you could do is you could just say, okay, I have a data set for each task, and we're going to take the union of those data sets into a single data set. And likewise, I'll take the loss function for each and just kind of sum and get a loss function. And now we have a single task learning problem where we have one data set and one loss function, and we're done. And in many ways, yes. Aggregating the data across the tasks and learning is one very successful approach for multitask learning, but we can often do better. And in particular, we can exploit the fact that we know the data is coming from different tasks and use this to achieve greater performance and basically exploit that structure in the optimization in order to perform better. Okay. Now, I think one of the last things I want to cover is why now? Why should we be studying this topic now rather than in 10 years or 10 years ago? Well, people were actually studying this problem a long time ago. So this is 12 years ago at this point, 22 years ago at this point. And this is by a survey in Rich Karuna thinking about how we can train tasks in parallel while using shared representations. You can do multitask inductive transfer and add extra tasks to a backpropagation neural network. In 1998, Sebastian Thrun was thinking about this problem, where we want to be able to exploit an enormous amount of training data and experiences that stem from one another, stem from other related learning tasks, in order to generalize to new tasks, even from a single training example. And actually, even earlier, in 1992, Sami Bengio and Yashua and others were looking about the possibility of learning a learning rule that can be used to solve new tasks. So these ideas are by no means new. People have been studying these for a very long time at this point. But I think that right now is actually a particularly exciting time to be studying these algorithms, because I think that they're starting and actually continuing to play a fundamental role in machine learning research, especially with the advent of powerful neural network function approximators, the amount of compute that we have right now, as well as the kinds of data sets that we're looking at. And so as some examples of very recent works that have kind of leveraged some of these algorithms to do well, here's a paper looking at machine translation across over 100 languages, thinking about how you can learn algorithms, and these algorithms surpass strong baselines that use only 2 languages. here's some work from my lab that I actually previewed at the beginning. Is we can kind of use these types of algorithms to learn from a video of a human. So this is actually one of your TAs who's showing a video to the robot of performing a task, and then the robot can use that video to learn a policy that can successfully place the peach into the bowl just from that single example, and the policy can generalize to different positions of the bowl. So we'll cover kind of the algorithms underlying this. And people have also looked at multi-domain learning. So in here, different tasks would correspond to different domains. And this paper, they constructed different simulated domains with different textures, different environments, and they showed that they could use only this data in simulation in order to enable a quadcopter to fly in the real world and navigate in the real world. And actually, just like within the past 2 days, this paper was published on how YouTube is using multitask and multi-objective systems in order to make recommendations and developing algorithms that can handle multiple competing objectives. So I think that these types of algorithms are playing a huge role in robotics, in kind of deployed YouTube machine learning systems, as well as in other research. And I also think that they're playing an increasing role in machine learning research. So if you look at Google search queries over the course of the past few years, we see a trend that looks like this, where blue is meta learning and red is multitask learning. And we see an increase starting around 2014, 2015. And if you also look at kind of paper citations for things that cover things like fine-tuning, we see an increasing trend. Meta learning algorithms, as well as multitask learning algorithms, we see that these algorithms are becoming of increasing interest, and I think that's because these algorithms are going to be really important in the future for enabling things like learning from small data sets, et cetera. And lastly, I think that the success of multitask learning algorithms and meta learning algorithms will be really critical for making deep learning more widely accessible. As I mentioned before, the kind of settings where deep learning has been very successful before are settings where you have 1.2 million images, 40.8 million paired sentences, 300 hours of labeled data. And in a wide range of settings, that's just not feasible. So if we look at, for example, a diabetic retinopathy detection data set, it has around 35,000 labeled data sets. I think labeled images, I think this is actually one of the larger medical image data sets. And yet it still has 2 orders of magnitude less data than kind of the data sets on the left, on the top. There was a really interesting paper that was looking at reinforcement learning for epilepsy treatment. In that case, they had less than an hour of data. And in some of the work that we've done in robotics, we've had less than 15 minutes of data per individual task that we want the robot to learn. So if we care about kind of making deep learning algorithms and the success of deep learning more widely accessible to these types of domains, then it's going to be critical to build these kinds of algorithms. And lastly, beyond the things that I've talked about, there's still many open questions and challenges in multitask learning. And I think that makes it a really exciting thing to study right now because there's a lot of problems to be solved. Great. So that's it for today. As a reminder, please do these 4 things. Please sign up for paper presentations, sign up for Piazza, et cetera. And on Wednesday, I'll be covering multitask learning and meta learning basics. I'll see you on Wednesday.